All right, well, let's jump into what I'm going to do is go over some of the old tests. It'll give you an idea of how long my tests are. Okay, and I included one that didn't have answers at the very bottom. Now, the problem is these tests are designed with 5 units as opposed to 3 units. So what we have to do is to add test 2 parts to get everything that's going to be covered on in your class in terms of unit 1. Hopefully that makes sense. Okay. There are 3 things that are going to be in every test. You'd be going both ways. You'd be naming a structure and you'd be drawing a structure from a name. Every test. Reactions. All reactions require 3 parts. You need to name all parts, their conditions, and if there's a mix, circle most stable. And lastly, some intermolecular forces. Every test will have these 3. This is the one that is the most important part, because to focus on it and review, because that's the part that most people find the most challenging. Okay, so here I have a structure. You get to name it. Now this is one of those benzene-based structures that is the, instead of calling this a benzene, it's based on phenol. Okay, so that automatically makes the carbon where the hydroxyl group is attached carbon number 1. We can either go clockwise or counterclockwise. Counterclockwise gives us the lowest number, so it's 2-ethyl dash phenol. Now, these were 6 points apiece. Say you said it was 2-methyl phenol. I would probably take off 1 point, assuming you got the carbon number right and you have the basis down. All right, another structure to name. Task number 1 is to find the longest carbon backbone. That includes the functional group. And the functional group is the hydroxyl group, the alcohol here. So we have to include that line right there. And then we're going to go this way. We can either go up or we can go straight out. Going straight out yields the longest number of carbons. So that's a 9. So that's a nona base. And because it's an alcohol, it's a nonanol. Now make sure you write that is an OL, not an AL. And it's got to look like an O. Then we have 2 branches. We've got a branch here, got a branch here. Okay, so there's 2-butyl, not 2, T-butyl. This is the branch here. T-butyl, and methyl. Now, on the test, I would probably not do a T-butyl. I would probably do an isopropyl. And look something like this instead. The butyls, there's like 5 of them. There's isobutyl, sec-butyl, T-butyl, N-butyl. And so anyway, and we don't run into those very often, so I'm going to back off on those. But you do need to know the propyls. That would be N-propyl. And isopropyl. That's supposed to be an O. So think of the isopropyl like a snake's tongue. If it was just N-propyl, that stands for normal propyl, it would just look like this. The 1, 2, 3. Okay. All right. So that's a nonal, and we're going to play like this is an isopropyl group here. So this would be five isopropyl, 2 methyl, 1 nonal. Okay. All right. Here we've got a cyclohexene. Now we can number this 2 different ways relative to the double bond. We can start here. We start here. We're going counterclockwise. So it'd be 1, 2, 3, 4, 5, 6. If we started up here at the top, it would be 1, 2, 3, 4, 5, 6, 8. And going clockwise gives us the lower numbers. Going the other way, it would be one 6-dimethyl cyclohexene. 2 plus 3 versus 1 plus 6, so that would be the one that is more accurate. Now, if you put this one down, I would take off 1 point. Okay, I mentioned careful on this one, mainly because of the possibility of a geometric isomer. So that is ethene, 2 carbon, unsaturated, and we have 2 benzene groups as branches, hence the phenol. So it's 1, 2 diphenyl ethene. And as opposed to that, which would be trans 1, 2 diphenyl ethene. By the way, Chem 31 was Chem 306 up in Washington. Okay, draw the following structures. Okay, we have a heptene, 7 carbons. Double bond starts at carbon number 3. So phenol is a benzene branch. Cyclopentanol Now you can draw this like that. I like to just draw it like a house. It's easier to draw. But you may draw it like this if you like. So it would be, I drop something there. Now you may number these and leave them on there. That's fine. In our class anyway. Okay, trimethyl cyclohexane. The two most common cyclic compounds are the cyclopenta and the cyclohexa, particularly the cyclohexa. It has to do with there's no bond strain. When you get into anything other than 6, you're starting getting into bond strain. In other words, instead of being the perfect tetrahedron, it starts to be something strained and isn't as stable. So that's why you'll see more 6-membered rings biologically than 5-membered rings. There are a lot of 5-membered rings too. I'm just saying though that between the two of them, the 6-membered ring is more stable. Okay, what is wrong with this drawing? Or this name? They don't match. No one sees any anomalies?
Is it missing a double bond?
I'm sorry, say again?
Is it missing a double bond on the number 2?
No. There's no double bond because it's not a hexene, it's a hexanol. Remember, OL is for alcohols?
It says 2-hexanol, so the alcohol should be on a different carbon, right?
No. What is this?
Should it be 1-hexanol?
Okay. This is a cyclic cyclohexanol, cyclic. And if this was going to be, they'd have to have a cyclo in there. So the way I drew this, it should be the way this is written, the cyclic one, is going to be three, 4 dimethyl cyclohexanol. So someone screwed up the key. All right, do you see why these aren't the same?
Yes, but there wouldn't be the 2 there anymore.
Well, in a cyclic product, no, because the cyclohexanol automatically makes the carbon that the OH is attached to as carbon number 1.
I see, okay.
I mean, you could say 1 cyclohexanol, and it would be redundant. If you did that, I wouldn't mark it wrong. I would just make a note of it for you.
Okay.
Okay, why does ethanol undergo hydrogen bonding? Well, you've got this OH on there. The OH is very polar. In my previous classes, I went into exact what are all the intermolecular forces per molecule. That's what these are here. But the main thing is hydrogen bonding requires an OH group. That's the main thing. And then the bonding, the hydrogen is partially positive, the oxygen is partially negative, and they attract one another. That's where the hydrogen bonding comes in. Okay. If we draw this out as written, we go butane, 4 carbons long. And then on carbon number 3, we have a ethyl group. Okay, but what we end up drawing, though, is really mislabeled. What we ended up drawing, it should be, so it's 5 carbons long, not 4. So it's going to be methyl pentane. Should have been, assuming that's the structure we were after. So be careful when you name stuff that you're not creating branching that should have been part of the backbone. Okay. All right, so we have an alkene. We have water under acidic conditions, so that water is going to add across that double bond 2 different ways. So normally we have a mix whenever we add water to an alkene with under acidic conditions. And what happens is the hydrogen, the hydroxyl ion goes across each side of the double bond. Each side of the double bond. Okay. Now this, what we're doing here is we're first adding water and sulfuric acid, and we get the products. Then we're adding an oxidizing agent afterwards. That's why this is worth 9 points. Okay, so the first thing we're going to get is a secondary alcohol. These are both secondary alcohols because there are 1 hydrogen here, 1 hydrogen there. So it's secondary alcohol. And we're going to get a mix. Which do you think is more stable, the left or the right? Kind of tricky. On this one, it would probably be the right one because the left one is more lopsided than the right one. So even though neither one is very symmetrical, the one on the right is more spread out. So the lopsidedness isn't as pronounced. Now on this one, I probably wouldn't mark either one wrong. This is kind of a tricky one. Okay, so now we have a secondary alcohol. We're going to throw an oxidizing agent in it. Means the secondary alcohols are converted to ketones. So that's what we end up over here. Right there. And to name these, this would be, it's a cyclohexanone. That means that automatically makes that carbon number 1. So it's going to be 2-methyl that's cyclic. Cyclohexanol. And this one would be 3-methyl. Cyclo. No. This is kind of a tricky one because it's a 2-stepper. So if your first reaction, you get a mix, all subsequent reactions after that are going to be a mixture as well. Did that one make sense? Okay, this one's simply name these alcohols. Okay, tertiary, secondary. No hydrogens here. One hydrogen here. How many carbon atoms does this have? First thing to do is draw it, which would be this here. So it's a cyclopentane. And there's a propyl group at carbon number 1. And an ethyl group at carbon number 2. And we need to count. So we've got 5 for the ring. And then we have 3 in the propyl group. With the ethyl group, 5 for the pentene. We have 10 altogether. Because our bodies are mostly water, which is a very, as you know already, a very polar solvent, it's important to understand intermolecular forces because they're going to interact differently depending on what they run into. For example, and we have our body's a big sack of water. So we've got to separate different areas of our body. And we do that by using nonpolar walls or membranes. The official name for those membranes is called a phospholipid membrane. But basically, the membranes are nonpolar. Everything else is polar. So if you're having a chemical reaction go on, you've got a nonpolar membrane, and you have a polar reaction going on here, and a polar reaction going on here. That's not going to happen. They're not going to intermix because you have a nonpolar membrane. That's why intermolecular force studies are really important when you get into biochemistry. All right, so now we have some reactions. Okay, whenever we have an acidic environment under 140 conditions instead of 180, we form an ether. And basically, ethers are attached via their OH groups. So you end up with this guy here. At 180, we're going to create an alkene. And this is going to create a mix because we can form water 2 different ways. Now, this is a particularly tricky problem here. I think it was too tricky for the class at the time. It's going to be too tricky for our class here. Basically, this can be had, this left-handed pentane alcohol, it's primary alcohol. You can get that with an alkene where the double bond is in the first two carbons. However, the mix you end up with is you cannot get this guy here. You need a separate alkene to get that one. So that's kind of a tricky one. I would not have something like this on your test. It's a nice problem, but it's too stressful under test conditions. Okay, so how do we want to make this? Well, first of all, it is a ketone. Ketones are made from oxidizing secondary alcohols. Okay, so we need a 1, 2, 3, 4, 5, a 5 carbon backbone with the secondary alcohol at position number 2. That's what this here is. Now, you guys are not asking any questions at all, so I'm assuming this is flowing okay. All right, we're going to have an alkene, and we're going to put hydrochloric acid in the mix. So that automatically generates a mixture. And the mixture is going to be a combination of chlorine going first position or the chlorine going second position. So that's the two products you get. And then the one on the right is more stable. It's got Markovnikov. It's got 6 terminal hydrogens as opposed to 5 terminal hydrogens, and it's more symmetrical. Here we have an alkene. We're putting hydrogen with a catalyst, a platinum catalyst, and the hydrogen is going to go across here. So that creates an alkane. This is a reduction process, by the way. So whenever you take away hydrogens, it's oxidation. When you add hydrogens, it's reduction. Okay, so that was Unit 1 test for my 5-unit class. Okay, and I didn't cover aldehydes or ketones in that class. That was Unit 2 stuff. Okay, so if we look at, let's look at this second one I had here. There's a lot of Unit 2 stuff on here. I need to do this one here. This is one that says alcohol, aldehydes, ketone review. And this has no answers in it, so let's add answers. Okay, so what do we got here? Well, we've got an aldehyde. And it is 1, 2, 3, 4, 5. So it's 5 carbons. So it's a now has 2 methyl groups. That carbon. Now, aldehydes are automatically numbered for you. Starts with 1, 2, 3, 4, 5. Okay, so we're looking at 2, 4 dimethyl pentanal. The line drawing version that would be okay, so this is a ketone. And it's a 4-carbon ketone, so it would be a cyclohexane. Butenol. Okay, here we have an aldehyde again here on the end, left side. It's a 3-carbon backbone, so it's going to be a Butenol. And it's got a benzene group as a branch and carbon number 2. So it's going to be 2-phenyl Butenol. Okay, so we've got a 3-carbon backbone primary alcohol. So that's going to be a propanol. Methyl 1 propanol. Okay, we have a thiol here. So this is going to be a cyclo into thiol. Sometimes you see it written like the bottom one there, cyclopentane thiol. This is probably the more common one. Okay, and here we go, name to structure. Butenol, that's 7 carbons long. Okay, and it's an al, so that means it's an aldehyde. And what is wrong with this, putting a 3 there?
Is it because the double bonded oxygen needs to be on the either front or the end of the molecule? It can't be on the 3rd position.
Right, because aldehydes have to be on the end, period. So either we need to change this to an ONE, make it a ketone, or get rid of the 3, one of the two. The way it's drawn here, we need to get rid of the 3. And we have 2. Oops. Butenol, 6 bromo, 2, 3, 4, 5, 6. You can also draw the aldehyde on the left side. That we go. That's just flip left to right. Both would be fine. Okay, what's the difference between aldehydes and ketones? How can you tell them apart? The aldehydes are, the carbonyl group is on the end, ketones are in the middle. And you name them differently. A ketone is named with an ONE. Aldehydes are named with an AL at the end. Okay, so Madison, does that answer your question? All right, everyone see why this is wrong with that 3 there? If you're going to put a number there with an aldehyde, you put a 1 there, not a 3. Can't be a 3. Three automatically means it's in the middle somewhere. And by definition, that carbonyl group in the middle is called a ketone. Ketone endings are O and E.
Professor, really quick question. When we're naming a molecule like this correctly, do we have to put the 1 there, or can we do dash heptanol?
One is totally optional.
Okay,
In some classes, they'll ding you for it, but I don't. I like it when people do that because it's consistent with all for other naming, so it's optional. Either way.
okay.
But with a ketone, you have to put it there because a ketone can be anywhere in the molecule. Can't be at the end, can't be at the beginning, it can be anywhere in between though.
So can you do one more example? Oh yeah, I guess there is an example of a ketone, just so we could see how it looks.
Yeah, a couple down. Okay. All right, so let's go on. Butenol, that's an alcohol. And notice I didn't specify where the OH group is. So that's 2,2-dimethyl. So if we were to put the OH group on the end, it'd be like this. But it doesn't really say where it is. So if I leave off a number, assume it's a 1. So in other words, assume it's a primary alcohol. Okay. Hexanone, cyclohexanone. Here we are with the hexes again. We have a 6-membered ring. And it's a cyclohexanone, so let's stick the carbonyl someplace. And that automatically means that's carbon number 1. So we need to go 1, 2, 3, or 1, 2, 3 down here. Either one is fine. Now, if you put 3-methyl-1-cyclohexanone, that would be fine. Unnecessary, but fine. I wouldn't mark it wrong.
I have a quick question.
Yeah.
So on something like this, so this is a ketone, right? So how would you find that out when it's in a shape? Because you can't really tell, like, oh, that's in the middle or on the end. If that makes sense.
Say again.
So this is a ketone, and ketones have the double O group, whatever it's called, in the middle. So on a shape, how would you determine that's a ketone, not an aldehyde? You can't really determine if it's on the end or in the middle, if that makes sense, on a shape.
A cyclic compound doesn't have an end.
So how would you say, like, yeah, that's a ketone? So how would you define that?
Well, how many hydrogen? Let's do this for the carbons. Okay. How many bonds does carbon have?
5, right?
4.
4.
Okay. So we have 1, 2 of the double bonded oxygen, and then a carbon-carbon and a carbon. So that's 4 bonds. Notice there are no hydrogens there.
Yeah.
Okay. A aldehyde has a hydrogen there.
Okay.
So the fact is that there's no hydrogen there means it's automatically a ketone.
Okay. So what if it's not written out with the carbons? How are you going to figure that out?
Well, you know, with line drawings, every time there's a kink, there are carbon there.
Right.
Okay. So then we have We do another color here. We have carbon, 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 oxygen double bond. So that's 4 bonds. That means there's no room for hydrogen.
Okay, got it.
Automatically makes it a ketone. Because that single hydrogen is required for it to be an aldehyde. Hence, you can't have a cyclic aldehyde
Okay.
unless you break up the ring.
Okay.
Now we're going to find with carbs, glucose is cyclic. But when it opens up and when it breaks apart, it becomes an aldehyde because its ring is broken. That's why carbs get very complicated fast. Okay, but for normal ketones and aldehydes, ketones have H's. Never. Aldehydes always have H's, no exceptions. Ketones, no H's, no exceptions, okay? All right, so instead of isobutyl down here, we're going to say isopropyl. So we have a pentanol. And it's at first position. And we have at position 2 isopropanol. In a position 4, we have 2 methyls. Okay, now this is unit 2.
Professor, I'm sorry, could you go back to the last example you just did?
Here,
Yeah. Yes, thank you. Hold on one second.
are you
Okay.
drawing?
Yeah, thank you.
Okay. Okay, so we have some reactions. Okay, so we have a, notice no H's. So what does that make that, a ketone or an aldehyde? Aldehydes have to have what? All the time.
The H, this is a ketone, right?
Yep, ketone. No H's. Or it's in the middle. Aldehydes are in the end, ketones are in the middle. Okay, so we have a reduction going on here. And remember, to get to a ketone, we had to oxidize an alcohol. So if we do the opposite reaction, which is a reduction, we're going to end up with the alcohol again, where the carbonyl group is. So this would be, oops. So this would be 2-propanone or just propanone because it can only, you can only have a position 2. So you get the 2 in this case is optional. So we have 2-propanone, reduced environment ends up with 2-propanol. And this would be a secondary alcohol. So ketones come from secondary alcohols. Aldehydes and acids come from primary alcohols. So here we have the same ketone, propanone, under an oxidative environment. So ketones cannot be oxidized, so no reaction. Here we have two butenol under 180 degrees acid conditions, sulfuric acid. So we're going to end up with that too. So that means it's going to be an alkene, and we're usually going to get a mix. Basically, we get a double bond on either side of the OH group. So if we draw this, let's see this inside. And the alcohol is there. Yes, I will put this on Canvas. The problem is I have to create a PDF file from this, so I don't know what should be harder, create a PDF file or just redoing it on a piece of paper, but anyway. So yes, send me an email to remind me. Okay, so we have two butanol, and we're gonna get a double bond on either side of that OH group. Okay, so get a double bond there. And we get a double bond there. And which one's more stable, left or right? So how many terminal hydrogens we have on the left? Oh, we have 3, 2, that's 5. And on the right, we have 3, 3, there's 6. And it's also more symmetrical. So we have more of those. Okay, we have ethanol. And it's being oxidized, like in a breathalyzer test for DUIs. Okay, so is this what kind of alcohol is this? Primary, secondary, tertiary? Right, primary. So when primary alcohols are oxidized, we end up with the aldehyde. So this would be ethanol. And then we're going to continue on to the acid. You don't need to label it acetic acid, you just put acid there, it's fine. So remember, primary alcohols, because there are 2 hydrogens, be oxidized twice. Remember, oxidation is the loss of hydrogens. Okay, we have another alcohol. What kind? Primary, secondary, tertiary. Right, it's tertiary, so no reaction. Okay, this guy is exactly the same problem as that first test we went over. Because we're getting low on time here. So just look up at the first example, exactly the same thing. Basically, we're going to add water across that double bond, we're gonna end up with an alcohol. And then alcohol is gonna be oxidized to either an aldehyde or ketone. Okay, so this is tertiary, secondary. We don't do mechanisms, lucky for you. And this is unit 2. And we're all done. So today in lab, I want everyone to just work on those worksheets those extra worksheets I put up. You can work on, feel free to use the board if you like, the whiteboards up front. You can work in groups. You can work at the tables outside. I just want this to be as productive as possible. Okay. Okay, take care, you guys. We'll see you in a little while.
Professor?
Yeah.
The test is after the Monday wet lab, right? The week after?
No, it's going to be, the wet lab is the following week. So the test is just the test.
So it's next Monday?
Correct. Monday or Wednesday, depending on what lab section you're in.
Okay, thank you.
And the Wednesday test is going to be different than the Monday test, just FYI. Do not switch sections though. If you're in a Monday lab, stay in Monday lab. I have to be very strict about this in terms of the test. Other than that, I'm much more flexible, but during tests, you have to stick to whatever lab you're assigned to.
Okay, also in general, do we need to bring our textbooks to class?
For Monday?
No, like in general, like in your class.
No, I'm expecting you to keep up in your textbook though. Your textbook does a really good job. I really like this textbook actually. I don't like the slides that go with it, but I like the textbook a lot. So no, one, your textbook is huge. And as long as you're keeping up in the sections. And the sections follow very closely to my lecture notes. Okay? Except, let's see here. They go into mechanisms a little bit. Ignore that. Like, for example, on page 441, talks about how elimination reactions occur. It's very interesting, except it's way beyond the scope of this class. So.
Also one more thing, you're gonna check the pre-write-up for the lab in 2 weeks, right? After the week of the exam, right?
Exactly. Yeah.
Okay.
And if you would get it done beforehand, you can show it to me. I'll be glad to give you some feedback on it.
Okay, thank you.
Okay, anything more? Doesn't sound like it. All right, see you guys in class. Or in lab, I mean.